Hello there, 8th graders. This is Mrs. Minowitz, and I'm here today to talk to you about the absolute age of rocks. So the first thing that I want you to do is make sure that you read the paragraph at the top of your notes handout, because it gives you some background information about what it means to be radioactive or what radioactive decay is. So if you need to pause the video, read that paragraph, and then come back. All right, now that you've had a chance to take a look at some of that background information, there's a few words and terms that we need to go through and make sure that we are clear on first. So the first word that you need to know is absolute age. So we already talked about relative age in class. Absolute age is slightly different. This time we are looking at the age in years instead of just which is older or younger. We are looking at actually coming up with a number to talk about how old rocks are. And the process that we use in order to calculate that is what's called radioactive decay. And using information about radioactive decay, we can determine how old rocks are and give them an actual number. So we're going to talk how that happens and also how we could actually calculate that. Half-life is another term you need to know in order to understand radioactive decay. And a half-life is the time it takes for half of a certain amount of radioactive material to decay. So in this amount of time, half of the radioactive material has decayed. And this can be a wide variety of time. With some elements, we are talking about less than a second. And with other things, we are talking about billions of years. And we'll take a look at, and we'll use some different examples in our calculations. But it can be a wide variety of time that we are talking about for things to decay according to their half-life. We also need to understand what an isotope is in order to understand this process. So isotopes are elements with the same atomic number or the same number of protons. That is the number at the top of the periodic table. So carbon, for example, if you look at it, is number 6. It has 6 protons. That's its atomic number. However, this is different from a regular atom in that it has a different number of neutrons than what we would normally expect to see in that element. Because we have a different number of neutrons, that means that the mass of this atom has also changed. Because if you recall from our first unit, the mass of an atom is based on the number of its protons and the number of its neutrons. So we're going to take a look at an example of an isotope. You have a copy of this on your sheet as well. One example here is, again, carbon. So carbon, if you look it up on the periodic table, has an atomic number of 12, or an atomic number of 6, and its mass is 12. Excuse me. So that means it has 6 protons and 6 neutrons. However, there is an isotope of carbon called carbon-14, okay? And it still has 6 protons. It has to have 6 protons to be carbon. But instead of having 6 neutrons, like our diagram shows, in the middle, it has 2 extra neutrons in the center here. Now, elements don't really like having extra neutrons around. They're not as stable that way, and they're not going to stay that way over periods of time because it's just not really designed, that atom isn't really designed to have that many neutrons hanging out there. So what happens, okay, for example, with carbon, is that those neutrons actually turn into protons and electrons. And over time, we get carbon-14 turning into nitrogen-14. One of those neutrons turns into a proton. When this happens, we can measure the electrons emitted in order to figure out how much of the carbon-14 do we have. What did we start with? This is called our parent material. And then what we end with is called the daughter material. So over time, we can measure how quickly this is happening and how much of this we started with and ended with, and we can determine how many have gone through and figure out the actual age of the rock. There are other examples on here as well. We'll take a look at some of the different half-lives of those different ones. Okay. Other words that you need to know are parent material and daughter material. So parent material is basically what you start with. It is unstable. It is radioactive. It is going to decay over time. The daughter material is what you're left with at the end, it is stable, it has already decayed, and it's not going to continue to decay because it's at a stable form. If you look at your paper, this chart here shows you some examples of isotopes and what they decay into and how long that takes. So for example, we looked at carbon-14. Okay. Carbon-14, over time, it decays into nitrogen-14. And one half-life for that process is 5,730 years. Another example, okay, is plutonium. Plutonium-238 here. Okay. It decays in 88 years. Okay, some are really fast though. Polonium, we're talking like parts of a second. So the half-life can really vary depending on what element you are working with or what isotope you're working with. You will notice numbers at the end of each of these isotopes. That has nothing to do with anything that we will calculate with it. It just tells us what the atomic mass is and lets us know that, hey, it's an isotope. Because if I write carbon, I don't know that it's an isotope. If I write carbon-14, I know that it is an isotope. So it's just to determine and show the mass and that it is an isotope. Now, one of the things about half-lives, okay, and I want you to graph this on your paper as well, is looking at how half-lives affect the amount of material that is left over time. So when we have 0 half-lives, we have 100% of our original amount remaining. None of it has decayed yet. It is all still radioactive. After 1 half-life, half of it is gone. So we could put a dot over here. I need to 50% of it is left. Now after 2 half-lives, we've lost a half of that remaining half, which means we only have 1/4 of it left, or 0.25. After 3 half-lives, we lose half of that again, and we are at 12.5% right here. Now, if you look at this over time, we can fill in this curve. It is an exponential decay curve here. It's going to go like this. And you might have seen exponential graphs before in math class. You will notice with my graph, however, that down here, okay, I never actually touch the axis here. It never makes it all the way to 0. And if you stop and think about that, you're going to realize that that makes sense. You can always take half of something. You can't take half of something and get 0. It's not mathematically possible. You can't divide by 0. Now, there does get to a point where you can't, it's so small, it's not really a measurable amount, and we would say it's essentially 0, but it never is completely gone because we're continuing to go half-life, half. There would still be some of it remaining. Now we can use this information and this idea in order to actually calculate the half-life of different, to calculate how old different things are using this idea of a half-life. So there's a formula that we are going to use. And to calculate what's called the final amount, okay, or the amount that is left to decay, okay, has not decayed yet, okay, so left to decay. In order to calculate that, we need to know how much we started with, and that is represented by P in this equation. So the original, or the starting amount, okay, is represented by P. The 0.5 comes from the idea that it's a half-life, and so we're using that as with our exponential equation here. And then T is the number of half-lives. And we can use this equation in order to calculate how much radioactive material is remaining, and how much has already decayed. So we're going to do a couple example problems here. We will be doing much more and with much more difficulty in class, but this kind of gives you an idea and kind of explains how to use this information. So let's go through here. So number 1 if you had a 100-gram sample of plutonium-238, how much plutonium-238 would remain in 88 years? The first thing to do here is cross off 238 because that is not a helpful number in here. It's just telling you that you have an isotope. So let's look at our equation. We have A equals P times 0.5 T. Okay. Now, it is asking us how much would remain. That would be the final amount, or A represented here. And it tells us that we start with 100 grams. So that would be P. So we know that P is equal to 100 grams. Okay. We have to figure out T, though. Okay. Because T is the number of half-lives. It didn't tell you how many half-lives here. It just told you 88 years. So we can set up a T-chart for the half-lives and the years. Now you need to go back to your chart and look at the half-life of plutonium-238, and if you look at it, it is 88 years. Now this is a pretty basic example, but I want to kind of show you how to set it up for things that are more complicated. So in 0 half-lives, we've had 0 years pass. Nothing has happened yet. In 1 half-life, it would be 88 years. Okay. So hey, that's the amount of time they're talking about. We know that our half-life is equal to 1. So we would say, hey, T is equal to 1 half-life. If we put that back into our equation, 100 times 0.5 to the first power. Okay. Then you can go ahead and put that in the calculator. Okay. Remember to do your exponents first, or to the first power, which is 0.5 times by 100, and you get 50. So your answer here, okay, would be 50 grams. There are 50 grams of plutonium-238 remaining. That also tells you that you have had 50 grams that would have decayed because you started with 100. Okay? Let's go ahead and do number 2 here. If you had a 100-gram sample of einsteinium-253, how much einsteinium-253 would remain in 40 days? Okay, I'm going to cross off my 253s. Okay. If I look up at my equation up top, I can read through and figure out that, hey, again, I'm starting with 100 grams. And again, I have to figure out how many half-lives have passed. And over here, we're talking about days. Okay? So I'm going to set up my T-chart, half-life, days. And if I look onto my chart, I see that the half-life is, where's my, over here, einsteinium-253, is 20 days. So 0 half-lives, 0 days. 1 half-life would be 20 days. 2 half-lives would be 40 days, and that's as far as we're going there. So we have 2 half-lives. We know T is equal to 2. If we put that into our equation, A equals 100 times 0.5 to the second power. And when you go ahead and put that into your calculator, I take 0.5 to the second power. I get 0.25. I multiply that by 100. I get 25. So 25 grams is left that has not decayed yet. We will go through this and many more examples with these calculations in class.